Okay, so part one here of homework 8-4. So question one, they ask us which of the following have the same period. And really, just getting comfortable with these functions, right? I do want you to start to get more comfortable with functions. They show us both displacement and time, but for the period, we're just focusing on the part that has time involved, right? And so if they have the same period, the aspect that involves the time is either 2 pi frequency times t, or 2 pi over the period times t. And so anything that has that same coefficient, that same number in front of t, is going to have the same period, right, in order for this end result to be 21 or 42. So don't overcomplicate this question. I actually don't have to solve anything to get this. I just have to look at this and see which ones have the same coefficient. I'm not worried about if it's positive or negative, just looking at those numbers. So 1 and 3 both have a coefficient of 21. 2 and 4 both have a coefficient of 42. Those would have to have the same period. So my option is A, right? Those both have the same period. Question 2, also hopefully not too bad. They do give us two different graphs, one representing the displacement of the wave versus time, the other one representing the vertical displacement, right, of the wave, the amplitude of the wave versus its position. So gives us both of those graphs, and then it does ask us what the wavelength is. Again, this one's not a overly complicated question, just making sure you can interpret the graphs pretty well. So if I look for what the wavelength is, well, I'm actually looking at the bottom graph because I'm looking at how long is the wave, right? I don't care about the period. So I'm just looking down here from crest to crest, right? That would represent one wavelength, and that is close to about 3 meters, right? So that's definitely the closest option. So the correct answer on this one is B, right? It's about 3 meters. Question 3 here is only difficult because it is difficult sometimes to remember the equation. But when we're talking about the the velocity of a wave as it travels down a string, the equation we're looking at is the velocity equals the square root of the tension divided by the linear density, right, the mass per length of the string. So they tell us that all of a sudden we've added a second weight, right? A second weight of W is added without stretching the string. And that part's important because if the string doesn't stretch, then the mass and the length of the string are not changing. So this is a constant number. So by doubling the weight, the only thing that I'm changing is I'm increasing the tension, right? If originally I just had one mass, so I had the tension pulling up, the single weight pulling down, if all of a sudden I double that weight, well, obviously as I double that, I'm going to have to double the tension then pulling upward because that string is not stretching, right? So the tension doubles, and then what does that do to my velocity? Well, since I'm increasing the top by a factor of 2 inside the square root, that means I'm going to be increasing by a factor of the square root of 2. So the correct option on this question is also option B. Again, hopefully pretty easy to work your way through. Okay, on question 4, I accidentally cut off the options, but that's okay. It's just option A is graph A and B is B and so on and so forth. Right, so in the figure, which of the curve best represents the variation of the wave speed as a function of tension? Well, that's the exact same equation we just saw for question 3, right? So the velocity as a function of tension is this equation right here, or if you prefer, tension divided by mu, which is the linear density, right, of the string. So if I look at this equation, I'm plotting velocity versus tension, and it is, if I look at just that, it's a relationship that relates to the square root of the tension, right? So the velocity, which is my output value, relates to some constant, right? So some constant number, I'll just call it A, times the square root of t, since my linear density is constant. So I just have to think about which of these graphs would best model the square root of t. Well, obviously, it's not going to be any of the linear equations, so AC, those are both out. E is going to be out because it doesn't curve downward. So really it narrows down to B or D, and B is the graph that follows the square root curve, right? It's a square root function if it looks something like B. D would be more like a quadratic function or an exponential function, so that is not the correct one. So correct option for this is option B once again, as we've seen on the first couple questions here, but making sure you're pretty comfortable with this equation is all we're doing on questions 3 and 4. Alright, so question 5 here gives us a relatively complex, right? It gives us our displacement for the position and time function. And it actually ends up being a pretty easy question if we just keep it simple. Right? What is the minimum time for each complete cycle of the wave? That's another way of basically saying what is the period of, right, the cycle of the wave, what is the period of the wave. And to find the period, right, I'm just looking at the inside function here. So if I look at the inside, the 3.25 meters inverse, that acts as my k when I have my kx, and then the negative 7.22 acts as my omega, right, when I look at my omega times t. So which of those values, k or omega, which one has to do with the period? Well, the value that has to do with the period is omega, right? Omega is defined as either 2 pi times the frequency or 2 pi over the period. So as soon as I identify that, hey, this is just a representation of 2 pi over the period, this is a pretty easy solve, right? So 7.22t, and I'm not worried about the negative because the equation is already negative, right, by nature. So 7.22t equals 2 pi t over the period. Obviously the t's cancel out from both sides. I just need to solve for the period. So the period equals 2 pi divided by 7.22, which obviously ends up being a little bit less than 1. So 0.87 seconds is my period for one complete cycle. So hopefully part A was pretty easy to break up. Part B, pretty much the same type of thing, except they ask us to use the wavelength, right? So what is the distance between adjacent crests? So again, that's discretely they're asking for what is the wavelength of this graph, or of this wave, right? To find the wavelength, I take advantage of my k value, right? K is defined not as the spring constant, but as 2 pi over lambda, right? So that's how we're defining k in the context of this function. So 2 pi over lambda. So just like I did for part A, I'm going to set 3.25 equal to 2 pi over lambda, and then solve for my wavelength. So lambda equals 1.93 when I solve that out. So I've got my period and I've got my wavelength, right? Without too much trouble, I was able to find both of those. So then finally, part C asks us for what is the velocity, right? How fast does this wave travel? Well, to find how fast the wave travels, really nothing too tricky, right? To find how fast the wave travels, I'm just going to go back to my original equation that I've used before, velocity equals frequency times wavelength. I just found the wavelength, and I know the frequency would be the inverse of the period. So the wavelength is 1.93. I know I switched the order here, but then the frequency again is just 1 over the period. So I just need to calculate this value, and that is my velocity, and it ends up being about 2.22 meters per second. Okay, so 2.22 meters per second, and that's the velocity. So question 5 is a very good one for breaking up this function if they give it to us, right? Obviously we don't have to create the function, but it is good at helping us identify kind of the key features of this wave based on that displacement function. Question 6 is also hopefully not too bad if you keep it simple here. So at first it looks like it may be a lot of work. At first we're thinking maybe we're going to have to do the derivative to find the velocity function. And we would if they didn't ask for the maximum speed. But because they ask for the maximum speed of the particle on the string, we know that the maximum speed is going to happen, right, if I just use the function, if I just use v equals 2 pi a over t. Right, what this is representing is this is representing the transverse speed, so how fast a point is moving up or down, right, and this specifically represents what's the maximum that value can be. Remember, this equation came from modeling this wave, this spring type motion as a circle. So that's where this function is coming from. So although you could definitely do the derivative of this function and then use that to help you with the velocity function and then find the maximum, that's a little bit more work than we need to do. And I will talk a little bit more about that in case we had to, but the easiest way to do it is just identify the amplitude, which in this case is just that 0.002 out front, right? That's my amplitude, just by identifying that from the graph or from the function. And then to find the period, much like we did for example 15, or for example, 5, for question 5, right? So if I want to find the period, I'm looking at the part that is with t. The only thing I do have to be careful about is this pi actually needs to distribute to both of those, right? So when, like example 5, like question 5, when I look at that, it's actually negative 52 pi t, which I know would be equal to 2 pi times the frequency times time. So once again, like we've seen before, the time would cancel out, the pi's cancel out, so the frequency is actually then negative 26, and I'm not worried about the negative, so 26 cycles per second, which means the period would be the inverse of that, right? So 1 over 26. So I've got my period, I've got my amplitude. Finding the velocity, I'm just plugging those in, so 2 pi times 0.002 divided by the period, so 1 over 26. Obviously that just inverts that, flips that over, and I get my velocity to be about 0.33 meters per second. So about 0.33 meters per second. So again, if I wanted to do this in the slightly more complicated method, I could do the derivative of that function, right? So if I did the derivative of that function, I would end up with the velocity function being negative 0.0020, and then I'm doing the derivative of the inside. So I'm doing the derivative of the sine function first, right, the cosine function first, making it sine. So that part doesn't change initially. But then to do the derivative of the inside, I do need to do the derivative of the inside with respect to t, right? So doing that, I would then multiply this by a new factor of negative 52 times pi, right? Since that would be, if I distribute the pi in here, it'd be negative 52 pi t. So then the derivative of that would be a negative 52 pi, right? So all I end up doing then is multiplying this number out front by that. But then the maximum velocity would happen when this sine function was equal to 1, right? That's the maximum value sine could be. So I would end up with just this quantity up front times this number here, which if you check your math, that actually is completely equivalent then to what I already have, right? So the mathematics behind it is the exact same thing. So the maximum velocity, whether I use the equation or whether I just use this function here, which is obviously a little bit easier, ends up being the exact same relationship. So I do want you to be comfortable both ways, right? We would have to use this velocity if they weren't asking us for the maximum velocity, but were instead asking us for just some arbitrary velocity at some arbitrary point in time. So you should be comfortable getting this equation, but in this particular case, we did not need it. Okay, so question 7, a calculation-based question, much like questions 3 and 4 in the multiple choice. We're looking for the tension of the wire. There is a typo here, and I cleaned it up in this document. But the 34, which had the apostrophe S, should have been meters per second. I don't know why, some reason when I translated that from the online book to the Word document, it didn't translate right. But anyway, it should be 34 meters per second. So they're giving us the velocity that the wave travels down the wire at. And hopefully that jumps out as we can use the wave velocity on a string, which is the tension, I almost said period. The tension divided by mass per length, right? So they're asking us to find the tension, which is one reason I'm using this equation. They give me the velocity, and then they give me the density and the diameter, right? So how can I use those two to help me with the mass per length? Well, density is mass per volume, right? Density is mass per volume in this case. It's kilograms per meters cubed. But I want this to be mass per meter, mass per length, right? So all I have to do is think about how does the volume relate to the length. Well, if I think about a wire, as basically being a thin cylinder here, right? So I've got my wire, it's a thin cylinder. The volume of that wire, the volume of that thin cylinder would be the length of the wire times the cross-sectional area, right? It'd be the area of the base times the length of the wire. That would be the volume. So if I want to take the density that they gave me, which is mass per volume, right? And volume again is the length per cross-sectional area. If I want to take that and I want to make that just mass per length, I just need to multiply it by the cross-sectional area, right? So in other words, what I'm going to do is I'm going to take the 2,700 kilograms per meter cubed, and I'm going to multiply it by the cross-sectional area of that wire. Well, the area of a wire, if it's a circular wire, is pi r squared, right? So I'm going to find my radius, so I'm going to cut the diameter in half, multiply it by pi, and then again just multiply that whole thing by this number here. So multiply this by pi times half of the diameter, so 0.0023 when I convert that to meters and then to the radius, and square it. So I end up getting that the linear density, right, the mass per length ends up being 0.0449. And as soon as I find that number, it's easy enough to plug that in, to plug in my velocity of 34, and to solve for my tension. So when I do that, I should get a tension that is about 52. So about 51.9 newtons is my tension once I plug those measurements in. Okay, so a very good question for helping us find the linear density as we need to. So then the last question, question 8, asks us to find the maximum transverse acceleration. So I went ahead and did the second derivative, right? I'm starting with this equation. And then the key concept that I do want to make sure everybody's comfortable with is, if they ask us to find the maximum acceleration, the maximum transverse acceleration, we just have to realize that the maximum is going to happen when this whole sine function is just a 1, right? So when that whole thing is just a 1. So in other words, it's going to happen when I have just omega squared times a times 1. I'm not even worried about the inside of that function. So all I have to do then is identify my omega and then multiply that by the amplitude. Well, the amplitude obviously they give me, and then they give me a route to find omega because they give me the frequency. And omega is just 2 pi times the frequency. So ultimately, if I plug all of this in, my maximum acceleration, omega squared times a, so 2 pi f squared times the amplitude, and we end up getting 47,000 meters per second squared.